All right, now that we know the types of neurons and types of neuroglia, the concept is, how do I send signals? Because that's one of the biggest things in the nervous system, is able to send signals back and forth into different places. And it's all dependent upon the concept of cell membrane potential, the ability to move ions across the membrane and thus generate a current. And that current allows me to send a signal. That's one of the reasons why electricity and things like that can interfere with nerves or be used to sometimes stimulate them to work better. So you hear about medical techniques where they use nerve stimulation through electrical impulses in order to do that. It's all about the distribution of ions, inside and outside the membrane. By creating a difference between the inside and the outside of the membrane, I've created a potential. I've created the ability for, once I move those ions, to create that current. So ions are going to pass through channels at different rates inside the cell membrane. And based upon that, how fast that works, my cells can manipulate that to generate differences. Does it have to be positives on one side and negatives on the other side? No. It could both be positives. It's just more positive one and less positive someplace else causes a difference. So these little membranes work like this. You have these little channels in here that can regulate and control what comes in and out. Some are free-flowing, open all the time, like a doorway that's constantly open. Some are selective. Potassium ions will pass through easier than sodium ions will. And those are the two main ions that play a role in how our muscles work and how our nerves work, which is why they work well together. They're able to interact very effectively well. Calcium ions are the hardest passing because they're much larger, much heavier. It's hard for them to get through. They also play a role, but they really aren't as important in this case, important for muscles especially, but here not as much. Still needed for the cells to function correctly, but it's really these guys sending signals, potassium and sodium. So you start out just like in physics, resting potential, the ability to do something. So you have to have a difference between them. It's ready to go. The energy's sitting there, it's like a spring, it's coiled, it's ready to go. It just needs something to trigger it. So you're going to have potential difference. In this case, a separation of charge between 2 points, in this case, inside and outside the cell membrane. What's going to generate that is this what's called the sodium-potassium pump. As the name implies, it's going to move sodium-potassium inside and outside of the cell membrane to generate this difference. So it's like putting the rock on top of a steep cliff, and as soon as you release the little stick holding in front of it, it goes flying downhill. Put a heavy rock up there, it's going to roll faster. Small rock's going to roll slower. Kind of concept like that. Sodium-potassium pump, the potassium goes into the cell, and sodium goes out of the cell. They both have a positive one charge. So I'm generating a difference. If I went equally across there, it would be a problem. So what happens is, for every 3 sodium ions, you have 2 potassium ions that come in. So you push 3 out, bring 2 in. So you produce a difference in the charge. This creates a polarized state. So now I have poles, different charges in between the inside and the out. So they're uneven across that membrane. All it takes is something to trigger it, to cause it to go. So that resting state value, in the case of these nerve cells, is negative 70 millivolts. That's the actual potential energy difference between the inside and the outside. So you have this concept where you're generating inside and outside. This is your nerve cell here, the neuron. You have differences between, you're basically generating by pushing these things in and out. You're going to create a different state. Over time, you're going to see how it's going to get less and less. There's more out here, less in here. You create that difference. To change the potential, I need a stimulus. I need something to activate this concept. This is where a signal from a previous one is going to activate it. So one nerve is going to send a signal to the other one using chemicals, and those chemicals are going to cause a triggered effect. It's going to basically turn on the response, allowing everything to flow back in. It's going to affect that polarization. It's going to cause it to depolarize. So the membrane is going to move towards equilibrium. As it does that, it's going to create a wave-like of energy that goes down the neuron, the axon, the parts of it, the dendrites, everything. This builds into a threshold. Once you reach that threshold, then everything goes. If you don't reach the threshold, once you activate the stimulus, it doesn't do anything, it just sits there. It's kind of like having a big rock up there and you push it a little bit, but it doesn't really go until you get a big enough shove to make it start actually moving. So I've generated a difference here, and as it goes along, it's going to create a wave. I'll be able to register that on an actual graph. You can measure that movement, how it's going to do, the electrical energy change. So you may see these kinds of graphs when you're talking about people taking graphs of the brain activity or the nerve activity. You may see this on those kind of graphs. Produces an action potential. So that means you can actually do something. How fast it occurs? 1/1000th of a second for your nerves to send that signal and make it start to do something. That's pretty quick. That means you can do it quite a bit in a second. But once you do it, you have to immediately put the cell back to the way it was before, because if you don't, that means you'll have a gap or a lag in time before you can actually do another action. So you get repolarization. I'm going to get that membrane to go back to the way it was, so that the next signal that comes along, it's ready to go again. If you have too big of a lag there, then you're going to be slow in reacting to be able to get the next signal, because you're going to try 6 signals, but nothing's going to happen because there's nothing to open up anymore. So it has to be fairly quick. So when I do this, I produce an impulse, an action potential. That means that wave goes down and is going to cause it to send the signal forward to either send a signal to another nerve or send a signal to a muscle and cause something to happen. So I generate this little graph curve here where I've let it go to depolarization and I repolarized it. These are how I'm generating or seeing the energy being effectively used or sending an impulse as it goes along. Nerve impulses, as they travel, have certain ways that they work for conductivity. So for example, ionic waves flow down the membrane. So as it starts here, it's going to flow. Now can I slow that flow down? Yeah, I could. Insulation is going to slow it down a little bit, because think about it, if it's trying to curve by bringing stuff inside and out, from outside to the inside of the cell, if I have fatty layer on the outside, that's going to slow it down. It's going to make that wave slow down. So if I leave it open, it's going to flow all the way through very quickly, but the problem is, when you do that, anything on the outside can interfere with the wave and cause it to stop. So you can disrupt it very easily. So this is going to occur at repolarization. As soon as I repolarize it, that wave's already gone, and then the next one's going to go, and it's going to go after it, and it's going to go after it. So you can send multiple signals, one after the other, but there is a limit to how fast that time is, how long it takes to repolarize. So the waves are going to occur at different rates based upon that insulation, based upon all things like that. Unmyelinated fibers, about 10 meters per second. May sound fast, but if you think about that, that's the 100-meter dash in 10 seconds. Myelinated fibers, ones that are insulated, they're incredibly slow. Too slow to really count most of the time. Great for accuracy. Incredibly accurate, just not super fast. Even that's not that fast to think about it. If I traveled to 100 meters in 10 seconds for my nerve speed, I couldn't even run that fast if I actually tried, because even if I was quick enough, I wouldn't be able to do it. That's where this comes in. Saltatory conduction. Sometimes I have a shortcut. The shortcut is I can get up to 130 meters per second, over 300 miles per hour. The way I do that is I take those nodes of Neuron VA. I skip each of the different insulative areas, and it makes it pick up speed as it goes along. It's like taking the rock and skipping across the water to get it across there faster. It's going to make it bounce and go quicker. Is there a downside of that? Absolutely. That means you could interrupt and disrupt the signal, but it's going to go a lot faster than either of the other two methods. It's going to be the quickest way to get it there. It's just going to have the danger of losing a little bit of that signal. These are also considered all or none responses. Either the signal is sent or it's not. There's no halfway, there's no partial signal, a little bit of a signal, maybe a signal. It's either it does it or it doesn't. It has to work that way. Your muscles have to work that way. They have to get signals to make you do it or don't do it, but nothing in between. So again, here I see the wave occurring, starts at one spot and it moves down here, and right behind it you'll notice it's going back to repolarizing right behind it.